later, or do you want to do interactive questions during the talk, Anthony?
Yeah, of course.
Or which?
Oh, sorry. Oh, no, you can definitely feel free to ask questions during the talk.
Feel free to ask questions. Good.
Yeah, definitely feel free to interrupt either of us. It's always better when people are asking questions as they come up. But again, if you have questions at the end and they're maybe a bit more sensitive, then that would be a good time to save them too, and we can always cut that part from the video. But yeah, Bernhard, you should be able to share it now, and recording has started.
All right, thank you. So let me see whether I can share. Can you see the introduction to Daml?
Yep.
Perfect.
Okay.
So as I said, this is a relatively broad introduction, trying to give you a high-level understanding of the whole sort of Daml technology suite. And really, what I'm trying to get across with this is what sorts of problems you can solve with Daml and how, so you can decide whether it's the right tool for you. But it's a half-hour talk, so I'll really only be able to scratch the surface. So hopefully this will serve as a sort of a basis for conversations later in this session. The structure of this talk is really around the sort of why, what, how. Firstly, just talking about the problems. Why should we even sort of care about this technology? What problems does it solve? Then a little bit of an abstract sort of description of the solution, our overall approach to solving the problems we described in the first section, and then the last section is really the slightly deeper dive into the Daml technology and how we actually realize that solution. Starting with a why, it really boils down to silos, data and process silos, which are everywhere, and how they impact digital transformation. Now, digital transformation is, of course, much more than a technological challenge, but many businesses do face very serious technological challenges in their digital transformation projects. And with Daml, we are solving, I would say, the biggest of those, data and process silos. Because if you think about what you need for a digital business, there are sort of three core concerns that silos are really in the way of. The first is you need access to real-time, consistent and quality data that you can use for analytics and decision-making. With the sort of fractured siloed landscape you get in most enterprises, you simply do not have a source of truth that you can use for that sort of purpose. Secondly, you need to be able to automate your processes, ideally even make them self-service so that you can compete on cost and speed with other purely digital businesses. And we are focused on the financial domain where such things are really common. If you need manual intervention or reconciliation as part of your business processes, you cannot offer that, right? You end up with multi-day slow processes. And the last is, business is accelerating more and more. But so if you really want to play in that sort of digital space, you need to be able to adapt with changing business needs quickly. But this is complex, almost to the point of impossible in many of the siloed application landscapes that enterprises have in place today. Yet, we're saying silos are sort of a real problem here, but they actually exist for very valid reasons. If you think about it, almost every business application somehow involves the processing of data across multiple parties, right? Across enterprises and business units within that, or even just sort of software services in an application landscape. And such parties typically need to or want to control their own records. So they create independent systems, silos, right? And this could be for organizational reasons, each enterprise really needing their own systems, regulatory reasons, or just technological reasons, right? Service-oriented architecture actually makes the choice very deliberately to decouple functionality as much as possible and sort of get some sort of composability. So in short, silos are created by multi-party applications in which multiple parties interact, but need or want to keep control of their own systems and records. And these types of applications are absolutely everywhere, both between organizations as well as within, right? Sort of, I've illustrated here a very simplified view of a doctor's visit or a patient visits a hospital, and there's an interaction with medical records registries, insurance companies, and the banks that ultimately make the money flow. But then we can also sort of go inside an organization like the insurance here, where you have different units and systems for policy, administration, claims, and finance, right? So even in this highly simplified view, you've already got what 10 silos or 10 parties that need to interact here. And the real picture is much, much worse. And this is, this exists in healthcare and finance and supply chain. Really, these multi-party applications are everywhere. And you don't need to take all this from us. Let's reiterate. Data and process silos are really the core technological challenge for digital transformation. Got a nice quote from Harvard Business Review here. The "our systems don't talk" problem, which bedevils most companies and is anathema to digital transformation, leads to enormous process inefficiencies, right? Core problem in digital transformation. Secondly, data silos are caused by parties acting independently, often for good reasons. So there's a nice quote from Gartner here. Business units undertake data and analytics projects individually, which results in data silos and inconsistent processes. And then the third point I made previously, data and process silos are everywhere. I found this nice statistic via Salesforce that according to the American Management Association, 83% of executives say their organizations have silos and 97% think they have a negative effect. Now, data and process silos are, in my opinion, really about business consensus, right? If we could keep all these silos in perfect synchronization, i.e. achieve consensus, I think there would actually be no problem, right? And our naive mental image of the world actually matches that idea. When we think of services in a service-oriented architecture, for example, which I consider parties on application in a business network, we often think of that local state in each of the silos somehow as being the local view of some global truth, right? So we think sort of our silos form some sort of nice landscape that are synchronized with each other. There's some things exclusive to silos and some things that are synchronized. But you all know that that isn't the truth, right? That naive mental image is false. In reality, each silo is completely independent, right? Synchronized somewhere in the business logic imperfectly. And we get this very fuzzy image, right? Where data is sort of colored by the silo it lives in. So there'll be data that is in multiple systems and is slightly different depending on which silo one looks at. And that imperfect synchronization takes a whole number of forms at the moment, right? So worst case, it's manual. We send emails, maybe with an Excel spreadsheet attached, maybe we manually type in data from a phone call or a PDF. And that typically happens between enterprises or the like. More and more, we automate this stuff via some sort of messaging, message queues, enterprise service buses, direct API calls with JSON and XML, but really all of that is just fancy machine email, right? We really still just send messages that we interpret at each of these silos. And lastly, and this has been a trend over the last 2 years, we try to synchronize after the fact. We put solutions on top of our stack, right? Integration platforms that try to glue together processes or the data. So as examples, we have things like API integration platforms, data warehouses or data lakes, etc. And especially with those sort of analytics solutions like data lakes, worst case, sort of basically just throw everything into a big pot and make the reconciliation the problem of the end user, right? If you want to analyze the data, you scrape it out of the data lake and have to do your own data sanitization. And the point the main point is that none of these sort of approaches actually solve the synchronization problem at the foundation. Synchronization using any of these techniques really happens close to the top of the software stack, far away from where the actual data lives. And that's where Daml comes in. That's what we're trying to change. With Daml, we're trying to really eliminate data and process silos in favor of composable networks of seamlessly interconnected business. Now, we need to give you an idea really how we're thinking about this. So to give you some idea of what Daml is, I'll first of all talk about the solution we're proposing in the abstract under the term virtual shared systems of record. What we're trying to do with Daml is really make that naive mental picture of multi-party applications that we saw earlier reality, right? Where those sort of the Venn diagram overlap nicely. But we said silos exist for a reason. So what we're trying to achieve is that data is still physically at and controlled by individual parties, A and B, sort of in their infrastructure. But we want to guarantee that these local systems these systems are kept in sync automatically and securely, so that for all intents and purposes, in particular from the developer's point of view, they are really just views into a global shared system. And that's why I'm talking about a virtual shared system of record. Virtual, because it doesn't really exist. This foundational layer is really an abstract concept that emerges from the synchronization of these towers. And shared, because for all intents and purposes, you can sort of pretend as if you're writing to a shared system of record. Now, most of the magic is in that phrase I just used, secure synchronization. Right, which we can now talk about. So the first of all, sort of in this picture, A and B somehow exclusively own some of the data and processes, right? Indicated here in the dark and light blue. But some of the data and processes indicated in the black overlap here specify how A and B interact with each other. There's somehow the interface between them that needs to be synchronized. And it's there where that secure synchronization needs to take place. And with that, we can really talk about what secure synchronization means. So the first I already sort of scraped over on the previous slide. The first one is about data ownership. We need to really specify who owns a piece of data or process. Is it really under A's control? Is it under B's control? Or is it something that needs to be co-owned, jointly governed? Is it part of the interface? The second is that we need to permission the interactions between our two parties quite strongly, right? When we're interacting in this interface, A and B need to have pre-agreed on the rules that concern the data and processes in that overlap. Thirdly, we need very good privacy properties, right? The data and processes need to be shared really on a strict need-to-know basis. It is often even sort of a requirement that A must never learn of B's exclusive data or that B learns of A's exclusive data. So these need to be really well isolated from each other. And the last is sort of isolation more on the security side, right? We really need to maintain that siloing that is the reason why people build silos in the first place. Parties mustn't be able to falsify each other's records, either through fault or malicious behavior, or deny availability of the system, right? A must be able to work on A's exclusive data, no matter what B does. And to make this a bit more concrete, what we're really proposing architecturally is this. At a very high level, most applications currently look something like this. You've got a data store, a system of record. On top of that, you've got a bunch of business logic, and often written in general purpose languages like Java or .NET. And you've got some integrations or UIs on top. And the synchronization that I mentioned before, if it isn't manual on the UI level, usually happens at the business logic level, right? We have APIs here connect to a message queue or similar, right? So it's sort of not at the data level. And what we're proposing is that you enhance the database with a virtual shared system of record. So you keep building your application using your favorite technologies like Java or JavaScript, but instead of directly talking to a database, you talk to the API of a virtual shared system of record, right? That API wraps the local data store and exposes data and processes as a view to this virtual shared system of record. And again, we're trying to sort of give a really easy sort of mental model there. So that API is really against that global state. So even though in reality you're talking to a local system, that API feels as if you're talking to this virtual shared system of record. Right? And the important thing here is if we look at the two slides next to each other, the synchronization has moved from the sort of mid to top of the stack, from the business logic really into the data and process layer where sort of the crown jewels live. And we really see this as the natural evolution in the architecture of enterprise applications. So if we look at this timeline, we've moved from entirely centralized models in the 80s and 90s, mainframe applications, to loosely connected models over the internet in the 2000s and 2010s, to distributing our IT infrastructure using cloud services in the 10s and 20s. We have iteratively broken down and decentralized our IT silos, right? So we are now on decentralized servers. The next logical step is to do the same with our data and processes. And virtual shared systems of record are the way to do so, which give rise to what I call here composable architecture. Now you may wonder, how did I jump from what I've just presented to composable? Well, basically, we've so far always looked at the picture with two parties, A and B, but hopefully it doesn't come as a surprise that the idea is to do this with many parties, right? And once you look at that multilateral situation, solving the synchronization problem at the foundation in the way illustrated here with this global shared virtual system of record has a really quite nice consequence, right? On the virtual shared system of record, the individual party silos compose into multi-party applications, first bilateral, then multilateral, and those applications that compose in the same way into networks of applications. And I'll go into much more depth on that later. If you think back to the doctor's appointment example where we had lots of bilateral interaction, right, between the patient at the hospital and the records registry and the patient and the insurance and so on, all of these bilateral interactions come together into a coherent application on this sort of composable virtual shared system of record. And this is really just down to the fact that wherever party or application sort of views overlap and interface, the data and processes are guaranteed to be in sync. So the composability really just comes for free. So let me tie the what that we've just discussed, virtual shared systems of record, back to the original section where I described the silo problem. What do you get with a virtual shared system of record? Firstly, you get that golden source of truth. If you can access the views of multiple parties, which can be multiple services or multiple teams, you're guaranteed to be able to reconstruct a consistent whole. So analytics data stores and audit trails across your systems basically come for free, right? You can always construct, always reconstitute a global truth. Secondly, the manual reconciliation just disappears, right? This really opens the door to highly automatized digital business processes. And thirdly, your systems become composable at the foundational layer. This allows for much more dynamic and nimble adaptation where you can reassemble and extend functionality with ease. And I'll talk about that in quite a bit more detail in the next section. So far, this has all been very abstract, I think. So it's time to bring all this back down to earth and really give you a glimpse of the magic source and how Daml is able to provide such a virtual shared system of record, which we usually describe as a Daml ledger. So first of all, let's go back to the core concern of secure synchronization of these overlaps in views. Just to remind you, those were about data ownership, permissions, and privacy. Now, these need to be agreed upon by the parties that want to interact on these systems. So this type of system actually needs a schema that describes those interactions, really just like a database needs a data schema. But a schema for a virtual shared system of record needs to capture all of these core concerns of secure synchronization. So we actually need a much broader type of schema, which in our case is the Daml smart contract language. So Daml takes care of the data schema in line with databases, but also of permissions in terms of ownership and read-write access, as well as the processes which describe how parties interact on the interfaces and modify that co-owned data. And I think it's time we really look at one of these schemas in practice. So the core concept in Daml is a template, indicated here with the template keyword, and it closely resembles a class in an object-oriented language. A template has properties, data properties that are stored on an instance of the template. We've got something very similar to methods. For those that have used them already, we usually call these choices, but you can really think of them as methods. Those methods have parameters with which you call them. And once you call them, there's business logic that gets executed. Now, the state of a Daml ledger is simply a set of instances of such templates. So if you're familiar with such things already, you can really just think of Daml as an object store where the objects are instances of these templates. But here comes the new part. The properties of your templates really are your data schemas. You can think of templates as tables and these properties as columns. Right? You may be familiar from other language ecosystems with sort of object database mappers, like for example, Microsoft's entity framework. But here there's actually no real translation to SQL in the same way. Really, Daml is your main schema language, and you actually store instances of these objects on your data store. The second really new aspect is that permissions really permeate every aspect of these templates. We've got a signatory clause here, which is all about data ownership. We've got an observer clause here, which is all about read access. And we've got a controller clause here, which is all about method access, i.e. write access. The third new part here is that the methods on these things are really your primary APIs. They are both how you interact with the system of record from the outside world, from your business application, but also how you assemble complex business logic within Daml, how you compose these objects into more complex logic. That's where you get to the last part. The method bodies, different to what you might be used from .NET or Java, are pure, meaning they have no real side effects. They're deterministic, and they allow the atomic composition of other actions, i.e. other API calls. I'll go into that in more detail later, but we can see several examples of that here, where exercise indicates a call to another method. Now, because the instances of these templates encapsulate really the mutual agreement on permissions and processes, we don't typically call them objects, but contracts, because they're really a contract of how we interact between multiple parties. And it is the deterministic nature of these methods and their atomic execution that are key to the system as a whole. If you think about it, if you can establish consensus on the order and validity of API calls, in this case, these onboarding calls, you get the rest for free, because from the API calls, their order and the validity, you can deterministically just rerun all the logic to get to the final state of your system. And that's why the Daml virtual shared system of record is at the core an event block. And I've illustrated that here using a cache issuance and transfer application. The system ensures that each party, in this case, we see Amy's here, keeps mutually consistent and valid event logs. And these can always be joined together into a virtual shared event log, right? So we've got Amy's event log here, where she sees events that affect her, right? So the Fed issued to $100, Tom transferred her $50, and then she transferred $80 back to Tom. And we can guarantee that if you had Amy's event log and Tom's event log and the Fed's event log and the Bank of England's event log here, you could reconstitute those into a consistent virtual shared event log. Here indicated with which parties see which of these events. And from those event logs, both the sort of the concrete local version as well as the reconstituted virtual version, you can get to the system state, right? From the issuance and transfer events, you can get to balances, both in terms of the local view as well as a consistent virtual global view. And the Daml language and execution model are really all about ensuring that the consistent ordering and validity of these individual parties' views guarantees global consistency. And that is the sort of the not so secret ingredient to the magic sauce. We call that the Daml ledger model, which is open source. You can, and very well documented. You can look at that online. And that design as a whole allows the Daml architecture to actually resemble that of the abstract virtual shared system of record that I showed earlier very closely. The parties local system is a component that we call a participant, which really consists of a stock database, usually PostgreSQL or Oracle, wrapped in an API called the Daml Ledger API, which exposes parties events, event logs and state to the parties. Which of course, as I showed in the previous slide, are at the same time their view into that virtual sort of shared event log, i.e. the virtual shared system of record. The big difference to the abstract picture is that the virtual shared system of record is here replaced with an actual concrete consensus and synchronization layer, which makes sure that the ledger updates are made atomically and consistently, right? So somehow the database interacts with synchronization services, which go into a shared consensus and synchronization layer, which then makes sure that everything works as it should. And because that's the role of that synchronization layer is really reduced to ordering and validity consensus, there are many, many types of systems that can solve this. And with Daml, we can abstract that away pretty much completely. And that is through a sort of a product we call Daml drivers. These exist for centralized databases. If you just want to sort of synchronize between services in one enterprise, you don't need all the sort of the low trust properties of blockchains or DLTs. But we also have drivers for blockchains, for distributed ledger technologies, for cloud platforms, and so on. There's a sort of an overview here of all the drivers that we've got. And the idea is that you pick these really entirely on your non-functional requirements, on the scalability, the resilience, and the trust context. You always get the same Daml Ledger API, i.e. the same sort of virtual shared system of record from your participant. So the applications that you develop on top don't need to worry at all what sort of driver they run on. From an application perspective, the drivers are entirely interchangeable, which then also removes the lock-in to these underlying technologies. You're no longer tied to a Fabric blockchain or an Ethereum blockchain or any of these other systems. And we sometimes parrot the Java mantra here: write once, run anywhere. But we don't stop there. We don't just stop at the Ledger API. We want to make it as easy as possible to integrate Daml into existing systems, or indeed build entirely new applications on top of Daml ledgers. So we've got this suite called Daml Connect. On the one side, Daml Connect is a suite of developer tools, both to develop Daml code, but also the client applications that consume the Ledger API. But probably more importantly, we're building out an entire application stack with which we aim to generically solve the most common integration, automation, and presentation tasks. Our aim with the stack is that many applications actually require no custom backend components at all, but simply configure and deploy Daml Connect as their backend. That is not to say that this is a walled garden. The idea is that one can take as much or as little of this stack as one wants. it provides numerous public APIs throughout, and the components internally only communicate via those. And then sort of the last offering you can get from us, which is again really in the spirit of making it as easy as possible to build on Daml. We've got our Daml Hub managed cloud offering, which tries to take care of the whole operational side. It's basically a fully managed cloud platform for Daml, where you get all the functionality of Daml Connect, plus a driver with some value-add integrations and application templates. And I like to think of it as serverless Daml ledgers and applications. So to recap the Daml ecosystem as a whole, we've got Daml drivers, which wrap up an underlying database, blockchain, or DLT, so it can act as the synchronization or consensus layer for Daml ledger. You have the participant node, which exposes the Daml ledger API, which is completely uniform across all Daml drivers. On top of that, you've got Daml Connect, which contains everything you need to build, test, and deploy applications on top of such a Daml ledger. And you've got Daml Hub, which offers the whole stack in a fully managed environment. And really, the whole stack is driven by this schema, Daml smart contracts. It doesn't just determine what happens on ledger, but through code generation and dynamic APIs, really it predetermines a lot of the functionality you get from this entire stack. So there's a lot of code reuse. Now, it's important to note here that the majority of this technology is free and open source. Drivers and Connect actually have community editions that are open source. Daml Hub has a free tier that you can use to get your application off the ground. And all of this is supported by a fairly lively community on the Daml forums, which is a really nice space. Now, at this point, what I've shown you actually only demonstrates how we're able to provide a virtual shared system of record, which inherently solves the data and process synchronization problem, which gives you two of the three benefits I touted earlier, right? A golden source of truth and reconciliation-free processes. So we'll have a quick look now at the how of the key third benefit I talked about already, which is composability. And for that, the example I want to take a look at is a sort of a simple one, which is we imagine we have two independent applications running already. One to transfer cash from one person to another, A and B here have their cash models, and one which allows user to record IOUs. IOUs basically just mean I owe someone some cash, right? It's a record of owing money. And what we would like to do is to compose these two apps into a slightly more complex loan application, one in which a lender can swap cash for an IOU from a borrower. What we need to do here is to add, first of all, add a new schema, right? New Daml templates, which we usually refer to as a Daml contract, Daml model. Now, the loan schema here depends on both the cash schema as well as the IOU schema, because of course, issuing a loan involves a cash transfer and the issuance of a loan or redemption of issuance of an IOU. The consistency properties of the Daml ledger, which again, sort of that's on the black overlaps here, already guarantee that where the cash interacts, everything is in sync, where the IOUs interact, everything in sync. So by putting on top here the loan schema, we suddenly get synchronization guarantees between cash and loans, and between IOU and loans, and between the loans of different parties. Right? So by entering into a loan, we're actually suddenly forcing synchronization between an IOU and cash, which wasn't there before. In other words, we have connected or composed these two previous applications. And this is done primarily by composing the processes governing those, right? I've indicated that here sort of with a mock loan template. Really executing a loan means atomically transferring cash in exchange for the issuance of an IOU. And we can see that very clearly in the code here. We've got this method or choice called grant, which means granting the loan, which takes as a parameter some cash. And I've noticed a typo there, need to fix that. And what happens in the sort of the business logic here, which is very abbreviated to keep it clear, is we exercise a transfer from the lender to the borrower, and we create an IOU, i.e. we issue an IOU, and then mark the loan as granted. And this is where the atomicity of this composition really comes in. We can guarantee that whenever a loan is granted, the transfer and the IOU happen together or not at all. And that is where the synchronization comes in. We can now guarantee that the IOUs and the cash used in loans always have both sides on ledger. The last thing we need to make sure is that all this translates into client application composition. And this is actually done architecturally. The lender and seller applications are independent and don't communicate directly here. So we've got A's and B's cash apps and A's and B's IOU apps. All communication happens through the virtual shared system of record. So just like synchronization of the data on the virtual shared system of record just required a new schema, extending our client application landscape here simply means adding new loan and, well, new loan applications for A and B, right? So composition with Daml is really an additive exercise. And that is the general theme of composability, right? To compose two applications, you just add a new one, which connects data and processes through a new schema that synchronizes at key points in the processes. And this is what brings the third benefit of sort of dynamically composable business processes and applications. Now, I'm almost done, but I'm going to call myself out here. I cheated slightly in the last section because I made a quiet assumption that maybe some of you already noticed, which is that the cash application and the IOU application live on the same virtual shared system of record. And you are all familiar with enterprise software. Things rarely live on the same IT infrastructure. So we have to make the assumption that actually the original applications we want to compose, cash and IOU, may live on different Daml ledgers. But this is where the second sort of composability comes in, which I like to call network composability. And this idea of them being on different Daml ledgers, basically we're just saying that doesn't exist. Conceptually, we think of all Daml applications in the world living on the same virtual shared ledger. Whether it's actually possible to connect or compose two applications using the techniques I showed you previously really depends on whether the parties involved in transaction share sufficient synchronization infrastructure. To make this concrete with a previous example, imagine we had cash transactions synchronized on the Fabric domain here, IOUs synchronized on the Postgres domain here. If the lender and seller are both participating in both applications, are thus connected to both synchronization layers, they can still compose this transaction into loans. In short, these two networks, as long as the individual parties share enough sort of connections, they form the same and a single Daml ledger from the point of view of the participating parties. Now, this sort of network composability is currently in alpha as part of what we call the Canton protocol. You can already download this, you can try it, but it's not quite ready for enterprise production use. But this is really where the development with Daml is going, to really form this more global coherent picture. And that gives you a glimpse into where the journey is going with Daml. We're delivering value today, providing these virtual shared systems of record on a range of different synchronization technologies. And in doing so, we're eliminating the core problem caused by data and process silos. But it's the composability of those networks that hints at our vision for the future, which is building a global economic network of really seamlessly interconnected businesses, where different financial institutions can really transact not only across regional and organizational boundaries, but also these network boundaries. And with that, I think I'm already quite a bit over time. I don't know when we started, so I'll stop here. Thanks for listening.
Awesome. Thank you, Bernhard. This is a great presentation, and no worries for going a little over. We've got plenty of time. So anyway, I'm going to share my screen in a moment. Let me just move a couple windows around. And yeah, if anybody has any questions for me or Bernhard in between or at any other point, feel free to ask. So 1 second, so I can set up here. Oh, geez. I don't know where my speaker notes have gone. So 1 sec. Ah, there they are. Okay, now we're good to go. Share my screen. All right, everybody can see my screen all right?
Yes.
All right, perfect. Okay, so this is a fairly interactive session, so I am going to ask audience questions during it. And so please, don't be shy. If you, I also have answers to every question that I'm going to ask. So if everybody is shy, we don't have to worry there either. And some people were joining earlier and may not have gotten my introduction. So I'll just reintroduce myself again. My name is Anthony Lusardi. I am a developer advocate at Digital Asset working on Daml. And from day to day, I'm just trying to show people Daml and get them interested and kind of explain what's interesting about it. And also, talk honestly about what the positives and negatives are, what the trade-offs are in different types of designs around these systems, because there's always so many things to consider whenever we're designing any sort of application. So today I'm going to be showing you UTXO and account models, basically the good, the bad, and the costly. So this is going to cover the two major types of designs that we often consider when we're talking about multi-party applications, blockchains, that type of thing. And I'm going to also be painting with very broad strokes. So even a single real world implementation of either of these types of concepts with the specificity that would be necessary to understand how that particular implementation works would take far, far longer than the time we have allotted. So as such, everything that I'm going to talk about in the first half is going to be very general. There's exceptions to every rule here. And I really just want to describe how these generally behave, because you can take that general knowledge about it and really apply it to a lot of things. But in the second half, I am going to dive a little more into the technicals and specifics of these two models in some real life examples and kind of demonstrate what the positives and negatives are there in a specific one. So first question I have for the audience is what is a UTXO and what is an account model? I just kind of want to gauge knowledge here. So, feel free to unmute yourself or type it in the chat. I just want to understand where everybody is at right now when it comes to these models. And if you don't know, then it's fine to say that as well. All right. So I'm going to take the silence as, we're all here to learn then. So a UTXO or end account model, both of them are any system of accounting or state management. And where they differ is how they manage that accounting or state management. In a UTXO model, every entry depends on previous entries. And so a new entry will consume a previous entry such that the prior entry can no longer be used. This is similar to, for example, $1. If I were to give you cash, then you would take the cash from me and I would no longer have the cash and I couldn't spend it again. Oh, and Abalash just mentioned that Bitcoin uses UTXO and Ethereum uses accounts. Yes, this is a great point and is actually something that I'll talk a little bit about later, but actually all of our systems largely derive from these original models, though there are some account models that I think existed before Ethereum, but not so much in popularity. And as far as the account side, on the account side, they tend to work more of how we imagine these things work in real life, and that is you're perpetually updating existing entries such that they can be accessed again in the future. And so what I mean by that is something that you would think of like a bank account or a credit card, is that you can give the same account number, the same credit card number over and over again, and more and more money can be taken out of it, or the same account can be referenced in any sort of way for everything. And so now to kind of think about it, does anybody know, I kind of actually gave it away, so maybe I'll skip this question, but there are lots of examples of non-blockchain UTXO and account models. Like I touched on before, the rough analogs of these things are things like cash and bank accounts, and they've existed for quite a lot of time. UTXOs have largely existed in the form of divisible and fungible bearer instruments, so that's cash, coins, gold, and all that, and accounts in the form of various types of ledgers that involve either single or double entry bookkeeping. So debt IOUs, bank deposits, these interesting, very old things called bulle, and things like credit card accounts that are also fall under the account models, and it's in the name. And when it comes to public blockchains and private blockchains as well, or these other types of ledgers where we're recording these things, you can kind of imagine that the UTXO side is very much these discrete units and the account side are these more general units. And bulle, even though I have them under accounts, they're kind of somewhere in between. There are these very interesting, though, double entry accounting where, as you can see, there's these little bones or rocks, and there's this clay ball on the left. And what people would do is they would use these little rocks to basically encode rights and obligations. And so the rocks would encode somebody's rights and the outside impressions would encode somebody's obligations. And you can actually combine these two things. So you would take the clay when it was soft, press them in, and then put these little rocks inside the clay and let it dry. And now you suddenly have this thing that you can't forge the outside of it and change what it says on the inside. And whenever a debt comes due, you can actually break it open and have it come due. And this is just a very interesting model that there's some resemblance there to the UTXO side as well. And so it's a great demonstration of the very funky nature of these things, how UTXOs can sometimes look like accounts and accounts can sometimes look like UTXOs. And it's just something to keep in mind as we go through this, but I thought it was a really excellent real world example of these things. And so that's kind of what the real life ones are. And so there's good and bad aspects of these models in the real world. On the good side for UTXOs is that once the UTXO versions is that you get, a high degree of privacy, you have a high degree of fungibility, you have very much easy guarantees that once something is transacted, there's no going back on it. Transactions essentially happen once. On accounts, they tend to be, fairly simpler to reason about, and they are generally easier to reference because you just reference the same account over and over again instead of referencing different stacks of coins or dollars or that type of thing. And one other interesting thing to think about is that when it comes down to accounts, we actually see accounts everywhere, not just in finance, but we see them, for example, you have social media accounts and email accounts and all that really are somewhat similar in those models, because you have these things that you can go ahead and reference differently. And also, if anybody has any other thoughts on what the positives and negatives are of these, then feel free to just, put them in the chat or unmute yourself and feel free to interrupt. And so now we're going to talk just about blockchains though, or rather multi-party systems is what I should be saying. And so can somebody maybe mention in the chat or over here, over voice, what are some examples of UTXO and account model based blockchains in your mind? And if not, Abhilash actually mentioned earlier that Bitcoin uses UTXO and Ethereum uses accounts, and this is exactly correct. We have quite a few of them, and the first real digital UTXO design kind of came through Bitcoin. And in this system, you have a wallet where you have one or more addresses that can receive one or more UTXOs and spend them later. And so along with some more critical parts of its design that enable people to freely and trustlessly transact money on the internet without any intermediary, this invention in UTXOs, in the part of the UTXOs, has really very much continued to spark considerable interest because it has a lot of other consequences that we'll see on accounting models and on safety and on how to do very good multi-party systems. And then after Bitcoin, we saw many more clones of this model. And then we also have accounts. And on the account side, really like one of the largest things we saw was Ethereum, where it made for much easier arbitrary state access and code execution, but it also led to a lot of bugs and very interesting things to think about that were kind of contrary to how we normally, when we're dealing with shared systems, we normally want to think of them as non-shared systems where we're in charge of the entire execution of them, and thus our bugs are only dependent on what we do or enable in the system, and that actually turns out to not always be true. And so I'll go into that a bit, but we have tons of other UTXO examples. We've got Fabric, Daml, and Corda that I've listed here. Daml, of course, runs on top of almost anything, but implements UTXOs in and of itself. And then on the account side, we also have Besu and Fabric. I've actually put Fabric in both because this is another great demonstration of how you can do both. Fabric is largely just key value store, so you can implement either type of model on top of it. Corda generally sticks to a UTXO model at its base layer, but again, has other parts that could be considered more accounts. So these things are fairly fungible in and of themselves, or interchangeable in some ways. And so on the technical side, we have quite a lot of positives and negatives of UTXOs, and it's all right if you don't know these. So I'm just going to go through them a bit. And obviously these also, some of these things are debatable. And so if you have any debates on them, feel free to interrupt and discuss, because there are quite a lot of things here. And so on the UTXO model, on the good side, we can say, well, they're more private by default. If I give Bernhard, for example, or Deepak a UTXO, only me and Bernhard need to care about the UTXO. However, in an account model, if I were to be spending from one account to another, every other account would also need to be somewhat aware of this transaction so that they can make sure I wasn't spending more than I had. That's not the case in a UTXO model. You can also prune the state significantly for that same reason, because every unit is discrete. Once it's used, that's it. It doesn't need to be used again. And if you see it again, it's obviously invalid. There's a general lack of arbitrary state access, which is, again, somewhat related to this. And that just removes a huge class of bugs. You don't have out of order execution issues, and you don't have other issues that we'll see later as well when I walk through the demonstration. And you also, I'll skip this next point, but you also get parallelizable operations because every entry is discrete. You can run multiple entries in parallel as long as they don't interact with each other. On the good side of the account model is you tend to, and some people would argue this, get smaller packets over the wire, which theoretically means less storage for your data. And you also, oh, sorry, can we just mute? You also get much more easy arbitrary state access. So sometimes it's very tempting to, you want to have the best kind of, I don't want to put this, you want to be able to write the richest application with the least amount of things in your way. And the account model is really good at that. Of course, having no safety guards can sometimes be a very bad thing, and we'll see that in a little bit. But it is, from some perspective, a positive. And also, account models really closely approximate how users and programmers think about these types of things, because that's how we envision the world, and that makes reasoning about them a good deal easier. There is always that little bit of thinking you have to first accomplish in order to get more comfortable with the UTXO model, whereas the account model comes a lot more intrinsically. I think that's what attracts a lot of people to it at first. Now, on the bad side, UTXOs constantly need to manage contention. Like I said before, you can only spend one once. So if two transactions simultaneously use the same one when you're actually trying to consume one of them, then you're going to end up in a place where you kind of have to figure out which one goes through and which one doesn't. And the good news is that only one of them goes through, but you still have to figure that out. And you also have to learn a new way to reason about the structure of your programs. And you also often end up with larger transaction sizes, because sometimes, like if I had a $20 bill and a $10 bill, and I wanted to spend $30, I have to combine them both. And that is a larger transaction size, because I have two things than compared to a credit card number where I have one thing. And that's the type of thing that you have to sometimes consider, but it's generally not too big of a deal in most cases. On the account model side, you get less amenable to state pruning, because you have to, every account basically exists into perpetuity. You never know when one's going to be accessed and by whom. Arbitrary state access creates a lot of opportunity for bugs, as we'll see in a little bit. And you also get reordering bugs and other things in there. You tend to get less privacy, because again, everybody needs to know about every other transaction to some degree in order to make sure that you're not trying to do something that you aren't allowed to do. And this also reduces down to single-threaded operation. So in an account model, every transaction coming in, basically, for the most part, I'm sure there are more advanced designs out there, but speaking generally, has to pause the execution of every other person's transactions, commit that transaction, and then go on to the next one, and can't really do much about that, because the order of transactions and the fact that you can affect any part of the global application state just necessitate that you have a single-threaded operation. And so that was the most in-depth technical slide. And now let's move on to actual real-world examples. So at their most basic, these models are just a way to reference data within a ledger. More commonly, they are kind of the address of an application and its associated data. And realistically, these two things can somewhat behave identically to each other if you program hard enough in order to do that. But in practice, they don't. And so in UTXOs, what we generally see on the left is that each discrete contract has its own UTXO. And within it, the account model, each generalized contract has its own address. One thing to note here too is that I'm presenting very simplified models here. So these, when you're looking at them, know that the things that I'll be talking about, they can get a lot more complex and they can leak a lot more information than you would expect given this small set of information. And Anant, did you have a question? Okay. So now I kind of want to think about some problems that can arise from these models like side channel attacks. So we can say the following happens. And just to give you a little bit of background, the side channel attack is where an attacker can basically use information they do know about a system to make guesses and predictions at information that they don't know about a system. And in some cases, even wholly uncover information they didn't know. So we'll say Carol and Bob are competitors, they're aware of each other. And Carol's working on your project under a strict set of NDAs. And you also haven't told Bob you're working with Carol because it's a sensitive project. Bob's also recently worked with Carol on another project. And Bob wants more work and wants to know more about your network in general. And Bob wants to kind of just bend the rules of your network so that he can find any competitive intelligence that, as Bob would call it, I'd probably call it spying. So in these models, what can Bob do to carry out his attack? On the UTXO model, first, on both models, we're going to remove the parts that Bob doesn't know. So this is actually Bob's intended view of both of these networks. And so Bob goes home, studies your distributed ledger and says, oh, within these models, I know that for these things, for that a particular job process to start, 2 transactions have to happen, one from you to me and one from me to you. So what Bob does is goes home and decides that, okay, I know these 2 pieces of information and it's a very trivial fact, so it's very easy to overlook. And Bob also happens to be working with Carol. And so Bob wonders if he transacts with both of you, can he figure out something that he doesn't know? So what Bob decides to do is create a contract with you and a contract with Carol and arranges these things so that they happen around the time that other contracts should be happening. And Bob says, well, if I could link these 2 things in some way, my transactions with you and Carol, I can maybe figure out some information about the network. Maybe I can figure out whether or not you and Carol are interacting as well. And that would look like this transaction over here. But Bob quickly figures out that in the UTXO network, these are all discrete units. And so there's no relationship that Bob can derive from these 2 transactions. In the account model, it's slightly different because Bob goes over here and says, okay, well, we have transaction 4 between you and me. And Bob says, oh, we have transaction 90 between me and Carol. And so that's peculiar because Bob knows that the last transaction he did with you was transaction number 2. And the last transaction he did with Carol's account, which I should be saying Carol's account and your account, is transaction 88. So where are the other ones? Where's transaction 3 and where's transaction 89? Bob can take a guess here now and basically say, oh, you might have recently started a project with Carol. And so the fact that each of mine are offset by 1 has leaked a little bit of information to me. And worth noting too is that this is a very simple problem. This is very simplified. In the real world, Bob, you, and Carol might have thousands, tens of thousands, hundreds of thousands of transactions going on in these networks, and lots of different opportunities for small bits of information to have leaked, not only at the UTXO and account layers themselves, but at the application layers that run on top of these models. And within the UTXO model, we just get a lot more safety here by default. In both models, you could program really hard and think really hard about your application and try and compensate for these deficiencies, for example, in the account model, but it's going to take a lot more work, and it's just going to be much, much harder to actually create secure systems like that. Obviously, I'm not saying that any system is ever 100% perfect in every way. I'm just saying which one tends to trend more towards this nicer security, and that's the UTXO model. So now we're going to get a little more specific and look at an interesting real life implementation, or very close to real life. And these are going to be in Ethereum and Daml. So again, we can compare accounts in UTXOs, and we're going to look at and basically a little bit of information leakage and an attack called reentrancy, which are neither things we want and tends to happen much more and really can only happen in an account model. So in practice, say we have here a program running on Ethereum, and the program basically allows you to owe someone a beer. And within that class, we have a few functions, and instances of this class will have these functions and also carry with them an internal state, like any program. And so what we have here are two functions. We have the owe beer function and the accept beer function. And so what we would want to happen here is that somebody who has a beer, say Alice and Bob are doing something together, and then Alice says, hey, Bob, I owe you a beer. And so Alice goes ahead, executes owe beer on the recipient, Bob, and over here we'll say, basically, if you can see my mouse, here's the proposal, and I want to owe Bob one beer. And then Bob can eventually accept the beer and say, okay, I will accept the beer offer from you, and say, basically, okay, well, beer is owed. We're going to increment it by 1. And then we're going to let everybody know that the beer has been accepted through running an event. And then we're going to have the beer proposal where we're going to deduct 1 from the beer proposal, such that the state over here on the left, where you have 1 under beer proposal of Alice to Bob, will go back to 0. And then that will make sure that when we're owing new beers, that it doesn't end up owing more beers than is intended from the person sending them. And Bob can also know that there's 10 beers owned, because this is a safety mechanism that we've kind of put into the system to stop execution at some point, so that Alice can never owe more beers than she owns. And the intended state is that Bob eventually is going to be owed 1 beer from Alice. But what we see actually is that something else happens, and this is not very good. So when Bob goes to accept the beer, because we didn't order our execution correctly, Bob can do this attack called a reentrancy attack. And so Bob goes and says, okay, I'm going to accept the beer. But before Bob's completed this call, Bob actually goes ahead and gives an address that does another call that basically says, oh, accept the beer again. And it re-enters, accept the beer again. And we are still trying to decrement the beer proposal, but we can't. And so Bob goes, accepts the beer, accepts the beer, accepts the beer 10 times until it explodes. And we end up hitting the limit of the total amount of beers that Alice actually owns. But in the meantime, Bob has basically escaped with Alice owing him 10 beers and having obligations to him that she had never intended. And that was all because 2 lines in our pseudocode here were kind of out of order. There are a couple of things in the pseudocode, by the way, that I kind of skipped over to simplify it for the slide, but let's just imagine that everything is there and it's executing truly. And now in Daml with the UTXO model, we kind of have the same thing, except we don't have to worry about that type of out of order execution, because what happens is every UTXO depends on other ones. So first thing is that Alice's beers owned doesn't exist, and Bob can't even know it, because each beer that Alice owns was purchased from a store and is owned as a discrete UTXO. So Alice takes one of her UTXOs and basically creates a beer IOU that says, okay, Bob, I want to owe you this beer. Bob goes ahead and accepts it, and then goes to exercise beer received. Bob, again, though, tries to do the attack and tries to say beer received many, many times. But what ends up happening is the transaction just fails because Bob exercises it, and the system goes and says, well, you can't exercise this more than once. You can have your 1 beer, but all these other exercises that just came in consume a UTXO that I know is already consumed and used. And so it explodes. Alice actually maybe gets to see that Bob's been dishonest and rebroadcast this many times, but luckily the state ends up entirely as we intended. And so that's another very interesting thing that can happen with regards to either of these models. And by default, in a UTXO is much more safe, and an account model could be made safe. You could order these things correctly and make sure you do a lot of due diligence. In any smart contract, you should be doing significant due diligence. But there's, to put it in the, it's much easier to have things go wrong in these account models, particularly where they're accessing very rich state, which you typically want in an account model as it is. And so, yeah, that's basically my presentation. And now we're happy to do Q&A if you have any questions about Bernhard's presentation, my presentation, or any questions about Daml itself. We're more than happy to answer. And yeah.
Hey, Anthony, so this example which you just presented, is this closely related to the double spend problem that we're trying to solve in UTXO?
Somewhat. The double spend problem is solved kind of at a couple layers. So really you're solving double spend most inherently at the consensus layer, where you're saying that I don't want the same exact transaction to happen twice. But in a sense, yes, you're also solving double spends here, where you're saying, I don't want 2 very similar transactions to happen twice. So there is definitely some minutia there, but yes, you do prevent certain types of double spending activity in a UTXO model by default, whereas in an account model, you wouldn't. But ultimately, it boils down to a somewhat consensus layer thing, if that makes sense. And if it doesn't, I'm happy to explain more.
So if I refer to that slide where you talked about the good and the bad between UTXO and account, in account, if I remember correctly, you had that everything is a single thread. So everything is happening one after the other. So is that in a way targeting this particular problem that we're trying to solve?
Yes, that would definitely be affecting that a little bit. But since it's one discrete transaction, you would almost, the threaded nature of it almost doesn't matter because it is all still happening in that one transaction. So over here, where we're re-entering, this is all really kind of occurring in one transaction. So it's not exactly the same thing.
Right, I get your point.
But no, that's a really, really good question. There's a lot of minutia there.
So what you're saying is, in essence, whatever the good and the bad that we can say on paper between UDXO and account model, in practice, that line is pretty blurry because I can model my system using any to mimic the other.
Yes, you can. In theory, you can model a UTXO system in an account model, and you can almost model an account, and you can definitely model an account model in a UTXO system. But in practice, it actually becomes very hard. And what you'll end up with is if you were to take an account model and try to make it as safe by default as a UTXO model, what you would find is you're basically creating a UTXO model inside that account model. So you might as well use UTXOs in and of themselves if you need that level of safety, basically.
Right, makes sense.
Yeah.
Hi, Anthony.
Just
trying to understand. So, the type of authority that Daml has in built in it, like the observers, the controllers, the parties, concepts, all those. Now, when it gets integrated with something like Ethereum, where you can apply various consensus mechanisms, proof of stake, delegated proof of stake, anything. So now, how does Daml fit in over there, where a different third-party consensus mechanisms has to be applied on that?
Yeah, so Daml can interface with any system that has an API or other way of talking to it in the much way most applications can. Ultimately, if you have, say you have a system that's part Daml and part Ethereum, and they're communicating with each other, and you have code executing on Ethereum, Daml cannot do anything to guarantee the safety of the code that's executing there on Ethereum. It can only guarantee the safety of the code that it's executing itself, and can only guarantee the safety of any data that's coming into the system from outside sources like Ethereum or some other database. But it still cannot fully provide safety throughout every layer of the system if you're doing things outside of it, like almost anything else. So yeah, your understanding there is correct.
So does that implies that if I develop a application using Daml with no other blockchain frameworks such as Ethereum, Skoda, or others being integrated, can I apply the different consensus principles within Daml somehow, or itself, like the way how Daml is built, or it will only be restricted to the theories that Daml has within?
Oh, okay. Yeah. So Daml actually has another way to do transactions. You can make them non-consuming, and in that case, UTXOs can persist, and they would function a lot more like accounts. So if you needed that type of functionality for certain things, you can definitely do it. And then, but even if you had like UTXOs that were generated out of those non-consuming transactions, you could still have them be consuming further down the line and make sure that everything still stays safe, if that makes sense. So you do have quite a lot of flexibility there. You don't have to worry too much about that because you still get that safety regardless.
Okay.
Utxo, maybe I'll add to that. If you remember back to my segment earlier, the consensus mechanism that you mentioned, the proof of work or proof of stake, happens at the very foundation of the system in what I called earlier the consensus or synchronization layer, which in principle can use any sort of consensus. You know, we integrate with some blockchains which use PBFT, proof of stake. I would say the only one that we currently don't target proactively is proof of work. The reason being that proof of work blockchains tend to be very, very expensive, right? And the sorts of applications that our customers are building tend to be targeted more at the enterprise. They are very high throughput. So proof of work consensus just isn't appropriate. But there's nothing in principle that would stop us building a a Daml driver for proof of work blockchain. In fact, we've sort of for fun and interest built Daml drivers for Ethereum, which we think would work on the mainnet. We just don't think it makes sense to do anything with them.
Okay, got your point. Thanks. Yep.
And Abulash had also asked a question in the chat about how does Daml on Fabric handle private data collection in Hyperledger Fabric? So I assume you're talking about Fabric's specific functionality called a private data collection. For Daml, we use basically the ledgers we're running on top of for consensus and synchronization only. And so the way you would do this in Fabric is you say your organization might run one Fabric ledger, another organization might be running another. You don't want to share all data between each other. We have essentially another layer called Canton, where your Daml applications don't need to change at all, but you can use that layer to guarantee privacy and get that much broader network interactivity that Bernhard had talked about in his talk. So that's kind of how we would handle keeping data private within Fabric and all other ledgers as well. When you're communicating, at those borders between different parts of a business that you don't want to share data between. All right, so I guess those are all the questions, but before you go, and obviously ask more questions if you have them right now, I would encourage you to check out bit.ly/try-Daml. Over there is our fairly active forum that you can find tons of information on. Daml at it. Sorry, I'm still waking up a little bit. You can find tons of information on Daml. You can go ahead and try out Daml yourself by installing Daml Connect. You can go to daml.com/learn, where you can try a variety of different tutorials in the browser. So if you wanted to get started with Daml, check out fundamental concepts, you can go ahead and run through all of these. They'll just execute remotely elsewhere, so you don't even need to install anything. We have excellent docs that really dive deep into Daml. Of course, if they take you too long, you can always hop back to the forum and ask a question. We have an introduction to Daml, which Bernhard has written probably almost all of it. It is excellent. It covers everything you need to know to learn Daml. It is how I learned Daml. So if you're interested, check that out. We have tons more videos that you can check out. We have a video training course right now that you can check out. We have YouTube channels and everything else. We even have a Hugel where if you're used to Haskell, you can go ahead and use it to query and figure out Daml functions in the same way as Haskell's Hugel. And certification, of course, where if you want to get certified in Daml, you can go check that out. And you can always, message me if you have any questions about it. And yeah, we also have links to Canton there, Daml cheat sheet, lots of stuff. I've just read the entire screen, but yeah, check it out. And obviously, if you have any questions, you can hop over to our forum. We're answering questions in there each and every single day. I already have a bunch of things to read this morning. So yeah, thank you everybody for attending, and thank you all for the very great questions.
So last thing, Anthony, like I just
Yeah.
wanted to know, like whether we will be getting this recording or this PPT that we have shared throughout the session.
Yeah, I'm going to save the recording now, and then I'm going to upload it on YouTube, and I'll make sure to email it out to everybody.
Okay, that's good. Thank you.
Welcome. All right. Thanks, everybody, and thanks, Bernhard.
Thanks, Anthony and Bernhard.
You too. Bye.
Bye-bye.